for the introduction, and thanks a lot for inviting me to give this talk. I will be talking about our approach to analog quantum simulations of quantum impurity models, and I placed this device, mechanical device, here on purpose, which will I explain at the end of my talk. So this work, let's see. Yes, this work, its experimental part of this work was done in the group of Vladimir Manchuran at the University of Maryland, and we had a very great theory support from University of Tel Aviv, Grenoble, Yale University, and University of Paris. So let me begin just by defining what the quantum impurity models are. So in very general sense, a quantum impurity model describes a local quantum subsystem, which is called impurity, which interacts with the bath of otherwise non-interacting modes. So the Hamiltonian of such system contains a non-interacting part, a bath Hamiltonian, which might be in general, for example, quadratic in creation and annihilation operators, and it has some size n. And then the impurity part, which acts on some subset of modes m, in general less than n, and it brings interaction to those modes. So the quantum impurity models, they're special because they are in some sense in between of non-interacting systems, which are easy to solve, and fully interacting systems, which are extremely hard to solve and maybe impossible to solve. And for that reason, first of all, there are some approximations which can be used to tackle some not so large problems. But then when you go to impurities which act on many modes of the bath, then problems becomes harder and harder, and actually the computational complexity scales exponentially in the size of the impurity. So the quantum impurities, it can be truly strongly correlated systems in this sense. Probably the most famous example of a quantum impurity model appears in the description of Kondo effect, which is an increase of resistivity of some metals. Here it's gold at low temperatures, which was unexpected. And this effect was explained in 50s by Kondo. So it has its name as an interaction of free electrons in the metal with individual magnetic impurities which are present there. And this discovery also led to development of Wilson renormalization group. As you see, this resistivity grows to the lower temperature, so it's reminiscent of renormalization flow where some parameter becomes more and more relevant as you go to the lower and lower temperature. There are many different examples where the quantum impurity models appear and useful. For example, they are used in description of impurities and interacting quantity wires, lateral liquids, Hall channels. Also, they appear in description of dissipative phase transition and so on. Another useful part about this quantum impurity models is that they're employed in what is called dynamical mean field theory, which is a tool used to simulate strongly correlated materials, where impurity basically is a lattice unit in this material, so for that reason, quantum impurity problems are believed to be a good problem for small quantum computers. So our approach is analog. So what we do, we use superconducting circuits, and we try to, for For example, here I show you an example of a quantum impurity model, which is a backscattering impurity in a lateral liquid, and it's our target system. And we use Josephson junctions to fabricate a system which will have approximately the same Hamiltonian as our target system. And even though this system might look complicated, it has some advantages of studying it instead of a real system. For example, you might have an easy control and fabrication of such system, and also it might allow you to go into regimes which are not so easy to access in the real system, the target system. So the goal for today, for my talk, is first to bring this mapping between two systems and also show you how we can extract information from this source system or simulator. So with this in mind, I will start first by introducing one main part of our setup is a high-impedance Josephson transmission line. Then I will consider an example of one impurity junction in the end and describe this inelastic scattering of single photons on quantum facelifts, which are at the core of our technique. And then I will go through two more examples of quantum impurity models, in particular boundary side grounded model and Kondo impurity. So before I go into details, let me just first give a quick introduction.
So can I ask a question just to make sure I understand?
Yes.
In the two transmission lines are going to model the bosonized version of the Lottinger liquid, and then the impurity is just a Josephson junction, correct?
Yes.
Okay. Okay. Thank you.
Yes, we use Josephson junctions made out of two aluminum films separated by aluminum oxide, and so in our circuits, we show them as a cross, and because these aluminum islands also have some capacitance, so this cross is always, or most of the time, it's shunted by a capacitor. So then the behavior of such junction is described can be think of like a behavior of a particle in a Washburn potential, which is given by this cosine phi and Josephson term. And the charging energy is analogous to the mass. For in our circuits, we use junctions in different roles. So for that purpose, I will roughly divide them in two big groups, large and small junctions. So by large junction, I mean that the potential is so high such that this imaginary particle sits in one valley and doesn't know about other valleys. So there is no tunneling. So in this case, you can estimate cosine phi just like quadratic, but just by its quadratic part. And so the junction behaves like an inductor. And because it has also capacitance, it forms a LC circuit with the typical frequencies between 20 and 30 gigahertz. And what is special about this inductance is it's a kinetic one, and it can be many orders of magnitude larger than the geometric inductance. And that's a way to create high impedance circuits. Then the small junction, I use the small junction when the tunneling between different wells is important. And this tunneling, its amplitude is exponentially proportional to a square root of ATJ over AC, where J is the Josephson energy of the junction and C is the charging energy of the junction. So in this case, the junction behaves like a truly nonlinear system. So first, let's look at the just Josephson transmission line. So here we use large junctions, approximately like 1 square micrometer in size, and they form two long chains, two parallel long chains. So here I have an example of 10 millimeter long chain, which contains about 30,000 junctions. So these chains, they support waves such that the voltage oscillates in between of two chains and the current flows along the chains. So these chains are shorted in this particular example at the end, at the right end, and at the left end they have an antenna which we use to launch those waves by coupling it to port of a 3D waveguide, a broadband waveguide. And then we use reflection spectroscopy to see resonances of this line. And when you do that, you see a bunch of resonances, which are the standing wave modes inside the line. And there are approximately like several hundreds of modes within 10 GHz. So the spacing is pretty small. And just from this fact, you can I see that actually the speed of light is very small. It's approximately like 2 orders of magnitude smaller than the speed of light in vacuum, which exactly a signature of the high impedance of these lines. So we can now count all those modes and from the very first one and plot a dispersion relation. So here it's shown in blue. So this dispersion relation has two asymptotes. So the first one at very low frequencies, so it's just linear, and it's linear. So the two chains behave like a transmission line, like a usual transmission line, and this capacitance in parallel to inductance doesn't matter too much. And if we introduce some a field phi and go to a continuum limit, then the description of this circuit can be given by this Lagrangian density, which describes acoustic type waves. And you can see that this is Lagrangian similar to a Lagrangian liquid. Of course, you might say that any transmission line will have that Lagrangian, but the important point here is this k. This k, it's called Lagrangian constant in Lagrangian physics, and it defines an interaction in an electronic system between electrons. And in our case, it's given by ratio of resistance quantum, which is approximately 6.5 kilo ohm, to the impedance of this line. And because we use Josephson junction, we can actually make this impedance very high. So we can go not only to a special point k equal to 1, where z is equal to 6.5 kilo ohm, but we can go as high as 5 RQ. So we can be in both in k less than 1, k equal to 1, and k larger than 1. So that's why we call it Lagrangian liquid, because that's why you need Josephson junctions. So then there is this saturation and dispersion to the plasma frequency, the highest cutoff. That's where this capacitance starts to play a role. And it's good actually for us, because we can now, by fitting this dispersion relation, we can extract these two numbers very accurately and get a value of impedance. So yes, so let's now see what happens if we add a Josephson junction at the end. So this small Josephson junction brings two types of process or dynamics to the phase across chains. So here I show you a Josephson potential with small junction, and first, so it brings a resonance. So there is a 0-1 transition, which is associated to this this phase at x point equal to 0. And second, there are quantum phase slips. So the tunneling events between different wells, which create a broadening of the levels. And this broadening, you can think about it in the similar way as appearance of dispersion on Q, where Q is a quasi-charge, is a charge which flows inside the junction. So if there was no junction at the end, then the photon would just bounce out of this boundary without any loss. So there might be some phase shift, but nothing else. But when we add this phase slip term, and here I show you Hamiltonian in creation and inclination operator just to get a better sense of it. When we add this cosine term, which is a dispersion of energy levels caused by the phase slips, you can see that this Q, it's actually contains contribution from all modes inside the line. So and you can straight away see that this cosine term will have many different combinations. Where, for example, one photon and mode k can be annihilated, and 2 and 3, 5, 7, and so on. Lower frequency photons could be created, just like shown here. Yes, at this point, I want to just make a quick note about this inelastic process. So, of course, there are many inelastic effects in nature. As soon as some sort of nonlinearity is present, photon will split. For example, high energy photons can split in the fields of heavy atoms. And there is this process of parametric down conversion, spontaneous parametric down conversion in nonlinear crystals. And of course, there are a lot of examples of nonlinear processes in circuits where usually Josephson linearity in quadric form is used. But what is common for all these processes is that the probability to split one single photon is quite small. It's 10 to minus 6 in this event, in this cases, and it can be a 10 to minus 4 here. And what is special about this cosine Q, what we found is that actually it can split photons with probability which is close to 1. And to understand it, let's look again at this decomposition of Q, which is a quasi-charge. So it contains contribution from various modes in the line with some prefactors Fk. And here on the left, what I show you positions of the mode. Those are measured positions of the mode in one of the devices, starting from the very first one at around 60 megahertz and all the way up to 7 and actually even more. And the length of these bars show the value of coefficient Fk. And what is special about this nonlinearity in Q is that coefficients Fk have not only a maximum around the resonance of the small junction of the impurity, but they also have this strong tail at the very low frequencies. So then there will be very efficient processes to split a photon. For example, if you look at this mode number 47, here on the right, I show you half of the measured line width of this mode. So it's very small frequency range. So all bars here are within just the line width of the modes 47. And then within this line width, there will be two very efficient processes where this photon can go. So first, it can go to the next one below, plus to the very first one, the very first photons. And also it can go to the second one below, and then for the very first photons. So both these combinations will create states with the same energy which is inside mode 47, and because their participation ratios are high, they will be important in this inelastic effects. But this is only two particular examples, but I can add all of them, and then you see that actually there are many states, multiphoton states, where this particular photon can go. And actually, you see that most of the photons within our transmission line, they start to interact, because actually after it photon decay to other modes, they still can continue these transformations. And what it reminds us again about the quantum impurities. Here we see that a local degree of a local subsystem, which is quantum impurity, present only at the end of the chain, creates interaction between many photons, many modes, which is again this a signature of a quantum impurity model. And what we can do, we can measure the rate of this decay, and from this rate, or in particular reflection coefficient of the impurity, we can extract many-body correlation functions which are different for different types of impurities. So how we do it? Let's me tell you, walk you through it. So this reflection coefficient of the impurity at the end contains two parts. It contains elastic part given by a phase shift, and it contains an inelastic part given by the decay. So we have this spectroscopy, which I showed you before, and for every resonance we can measure magnitude and phase, fit them, and extract line width. And this line width provides us this inelastic part decay rate. And by looking at the shifts of the modes, we can extract delta. So now we repeat this experiment at different flux points, and what we get is shown here. It's an example of an output of our analog quantum simulator. So here, every line it's a transmission line mode as a function of flux, and the color represents the photon loss probability per round trip, which is related to this R. And so as we tune flux, we see that the modes shift, and that's an elastic part of the impurity reflection. And also you can see that color changes. And here, for example, it becomes 0.9, which is close to 1. Now, if you take, for example, a cut, so we can extract from this data, again, extract the phase shift, which winds by pi around the resonance, and it has some line with gamma. And you see that there are many modes inside this line width, which is a signature of what is known as super strong coupling regime. And the super strong coupling regime is one of the requirements to see this effect of quantum impurity, or to be in this quantum impurity model regime. And second data which we can extract from the plot on the left is line width, and here I show you what it is without an impurity when it's detuned far away from this measurement window. So the loss is limited just by the electric loss in the line. And when the impurity is tuned to around 7 GHz, you see a peak in gamma, and this difference is effect of impurity, this inelastic decay. So we can see how it actually appears when we change the parameters of the impurity. So if the impurity is not strong enough, or the junction is not small enough, so the phase slip rate is small, then you still see a resonance, of course, because it's like a LC oscillator, but there is no effect on line width. So both with impurity and without impurity cases have the same line width. So as the impurity gets weaker, or junction gets smaller, you see that the interaction strength gets larger, and also there's noticeable effect in line width. To be more precise, we can look at the value of this gamma as a peak, and here I show you this value as a function of resonant frequency of the resonance for 4 different devices, all with impedances which exceed RQ. And for this particular regime, we were able actually to find analytical expression. This regime where impurity interacts not too strong. So there exists an analytical expression, and it describes very well the data which we see. This lines, the theory lines, they don't have any adjustable parameters. Their width comes from uncertainty in measured device parameters. And just for comparison, I show you here also what a standard phi to the 4 nonlinearity would give. It's many orders of magnitude smaller than the observed rates. And since we found this analytical expression and can and indeed confirm that what we see is related to phase slips, we can now move to a different regime. For example, make interaction stronger with impurity, and this can be considered as a verified quantum simulation. So now in this regime, there is no analytical expression, but this data in principle can be used to test, for example, some new numerical methods or something else. Yeah, so that's let me now talk a little bit about different impurities. So this technique, which I said.
Roman,
yes.
before we go on, can I ask a question?
Yes, yes.
So when you consider the impurity, you say that the small junctions behave as a facelift, but what if you just treat it as a junctions? Like instead of cosine 2 pi q, you just have like, cosine of phi. Does this still explain the data? I mean,
yeah,
it's just junction, right?
Yes, yes. Yeah, but yeah, of course, if you have cosine of phi, you can explain everything because it's that's the most full description of this junction.
So
but it's much more complicated. So this phase slip creates this term which is cosine q.
Yes.
And it's easier to treat it. It's also actually approximation. It's
yes.
This cosine q creates describes a shift in phase because this q is a conjugate variable to phi, and there is this pi in front. So this term describes just a change in phi by 2 pi, which is a phase slip.
But I imagine that if you have the junction, you must also kind of shunt it with some inductance, right? In order for it to behave as a facelift. Otherwise, if you just have a junction, it cannot be a facelift, right? Because like there's the phase is the.
No. If you have a cosine potential, then there might be tunneling, right? If you're in a regime where this tunneling is important.
Okay. So. Any small junctions can be treated as a facelift element?
No, not any. Yes, it's good point. So this description, which I talked about, valid only
yes.
if J over AC is not that small. If you have only basically phase slips by 2 pi. If you make junctions too small, then there will be different phase slip, for example, by 4 pi. 6 pi and so on, and then this description will not be valid, and actually the junction will behave differently. And I will talk a little bit about it.
Yes,
later.
I see. So actually, the ratio between your EJ and EC cannot be too small either. So the junction cannot be too small.
For this description, yeah. But when we talk just about phase slips, yes.
Okay, but when you have like small junctions, and you compare it with the large junctions, it behaves as a facelift. Because like you have the bosonic mode on the right, and then you have like the facelift impurity.
Yes.
Okay.
Mm-hmm. Yeah. Thank you.
Yeah.
And also I wanted to mention that if somebody of you recalls that this cosine q appears also in what is called a boundary Stein-Gordon problem.
Yes.
And it describes actually backscattering inside the Latinger liquid. So that's a connection of impurity Latinger liquid to a physics of small Josephson junction. But the difference only between this model and boundary Stein-Gordon model is that we also have a resonance. So if there were no resonance, it would be exactly a boundary Stein-Gordon.
Thanks.
Thank you. Yeah, so it's actually a continuation to what Long asked here. So this technique can be applied to different again impurities. So what we do, we just replace the circuit at the end. Everything else stays the same. We still measure reflection coefficient and extract we can extract correlation function. Here, as an example, I show you a system which is closer to boundary Sine-Gondran model, and it's achieved by making the junctions smaller. So this model is interesting because it also describes what is called a dissipative phase transition. So the small junction sees this Josephson transmission line as basically as a resistor, which is connected to it. And there is a prediction that behavior of this junction at the lowest frequencies is either superconductive or insulating, depending on the value of Z. So if Z is larger than RQ, then the junction is an insulator. And in our circuit language, it behaves like a capacitor. And if impedance is smaller than RQ, then it's a superconductor, and then the junction looks more like an inductor. And so by looking at the reflection coefficient, we can separate these two and try to go through this critical point and see a transition. So I will not go into too much details here, and it's still work in progress. I just wanted to share with you this this data, which shows an evolution of spectra when you make junctions smaller and smaller. So here, all these plots are spectroscopy data of two transmission line modes in a flux range from 0 to half. So here at 0 you have maximum EJ, at half you have minimum EJ, and this is the smallest EC or the largest junction. And you see that the modes are sharp everywhere, basically. And of course, yeah, there is this elastic effect, which I said. So when you make junctions smaller, you start to see a broadening. And that's exactly the broadening I was talking before in the previous part. When you make junctions even smaller, the broadening becomes larger. And then it's even more larger when you see as approximately 10 gigahertz. So all modes almost disappear. But then, interesting fact, if you go to even higher EC or smaller junctions, the modes become sharp again, almost sharp. We still see that there is a broadening, but it's much less than it was here. And what happens here is it's kind of a dual nature of a Josephson junction. So here at the smallest EC values, it behaves more like an inductor. But when you go to the very large EC values, it behaves more like a capacitor, and with a small perturbation given by J. And that's why you have this broadening now at 0 flux, where J is maximum. Yeah, any questions?
So I was thinking that you mean that maybe more like Josephson junctions behave like as a nonlinear inductor or as a nonlinear capacitor.
Yes.
And when it is like a nonlinear capacitor, which is like a very small junction, it's like a quasi-charged element, right?
Yes, exactly. Then the quasi-charged description is more relevant. Yes.
Yes. Okay. So as long as you make very small junctions, but if it's too small, then yeah, my understanding is that if you have a very small junction, it's just there's a quantum phase transition, no?
Yeah, if you have very small junction and your impedance is higher than RQ,
yes, you have
it's supposed to be in an insulating state.
Yes.
But of course, it's a theory, and it's true only at 0 frequency and 0 temperature.
I see. Thanks.
Yes, and so the final example I wanted to cover today is a quantum impurity. Again, same setup, different circuit at the end. And now the circuit it's a fluxonium qubit, so it has a small junction which is shunted by an inductor, and this inductor has two parts. So first, it's just an inductor which is in the loop, and second, this inductor which is shared with the transmission line. And the ratio between two inductances in the loop and shared can be characterized by this parameter x. So if x is 0, there is no coupling at all. If x is 1, then it's maximum coupling of transmission line to the fluxonium. And why this fluxonium is relevant for quantum physics is because of high harmonicity of fluxonium. So we use fluxoniums which 0 to 1 transition is very far detuned from any other transition. So it behaves very closely to a two-level system or a spin, and in this sense, it's analogous to spin in quantum problem. So here I show you a spectroscopy with of coupling, very small coupling. So it's only 7%. And here it's just a zoom out. And what you see again the transition line modes and this qubit 0-1 transition which passes through. And it looks more or less like normal, like what you see in any system. But what is unusual about it, and which was never observed before, is if you zoom in, you will see an extra anti-crossings on top of this main one. And this extra anti-crossings, they're exactly multiphoton states, which I was talking about before with a small junction physics, which we can now resolve because of this high harmonicity of the qubit. So, for example, this one here, it's caused by anti-crossing of mode 44, or we call it polarity trans. So this mode 44, it has a photon occupying state 44, and then this one which anti-crosses it, it has it's a multiphoton state made out of photon in mode 43 plus photon in mode number 1. And then this one is made out of, again, polariton 43 and now two modes in two photons in mode number 1. This one polariton number 42 and one photon in mode 2, and so on. So those are those multiphoton states which I talked before, but now you could directly see how they crosses with transmission line modes. And what happens if we make the coupling stronger? Here, for example, this x is equal to 0.5, and you see that there are now many anti-crossings everywhere. And if you go to the maximum couplings, those anti-crossings, they basically merge, and they create just a very broad modes. And what is interesting, at least if you look at in this region where it's not completely destroyed, the modes are Lorentzian, so they can described by a circle in the real and imaginary plane, and this circle shrinks, indicating that it's still Lorentzian, but this quality factor, its internal quality factor, gets lower and lower, and you can see it here. These black dots are internal quality factor. So through this anti-crossings, eventually, if you make them too many, and there are many multiphoton states where a photon can decay, it basically becomes just a broad line. With this, I would like to summarize my talk by saying that collisions between photons and highly nonlinear circuits can result in a single photon decay. And this decay can be very efficient. It can reach probability close to 1. And we can use this data, the decay data, photon lifetime data, to simulate quantum impurities in different parameter regimes, which might be not available to other systems. And finally, like an idea or a proposal where it can also be useful it can be a resource for testing digital quantum computers. So with this device I showed you at the beginning, it's a slide rule. It's a mechanical device which is used to calculate non-trivial to do non-trivial calculations like logarithms, square roots, and like in last century we could use this to verify outputs of a digital computer, electronic computer, and here it's our device is in some sense an quantum slide rule, and it can be in principle used to check if a quantum computer, small quantum computer, which simulates the same problem, outputs same result or not. So yeah, thank you for your attention.
Thank you very much, Roman. Are there any questions for our speaker?
I have a question. So on this last point, have you thought like what kind of algorithms can be used to simulate this quantum impurity, like some related algorithms on universal gate-based quantum computer?
Yeah, I know that there are proposals how to simulate quantum impurity models on universal digital quantum computers. I don't think there are any attempts to do it, but in principle, yeah, it's possible.
How many qubits do you need to simulate this problem?
From what I heard, it's around 100.
100.
To make something like reasonable or useful. Yes.
Okay, thanks.
Do we have any other questions? If not, I'd like to say thank you again and offer our warm affection for your talk and appreciate your time. Thank you so very much.
Thank you very much. It was a pleasure.